Hello. Good evening. What time is it? It's only 5 o'clock. Okay, shall we get started? Let's wait for 2 minutes. See if we still have any other students. Okay. So today we have 2 stuff. The first one is to have a review of the congestion control because the LAB5 is related to this part. And we will have a look of the question and exercise of LAB5 and solve the problem together. So let's come to here. Could you please just open the slides we have in week 5? I will also copy the link into our chat. So could you please open the slides here in case you need it? So we will go through the content related to the congestion control. We will start from page 84. We will just have a very quick look of it to make sure we can understand all the stuff. So the keyword is what is congestion control and why should we use it? And what is the CWND and slow start and AIMD? And what is the flavor of congestion control, including Tahoe and Reno? So if you have any confusion of these keywords, for example, you don't know what is CWND, probably you need to pay attention to it when we talk about it. Okay. So let's go to the first one. Why and what is congestion control? The slide page is 80. So as you can see, slides here, you can consider this graph is showing our bandwidth and the workload. So in here, we are trying to utilize the bandwidth of our internet because we can say our bandwidth is 100 Mbps, but our computer does not know what is the exactly maximum bandwidth of us. So it will try to reach this point, the maximum speed of it. But how can we reach this point? But because if we have too much load, like in here, the speed will be very slow because it's the traffic is congested. So that's the reason why we want to have the congestion control, because if we have lots of packet in our internet, and the router probably will not work, and all the packet will be dropped. So our target is to find this point and keep our workload at this point. So we will have the maximum speed that we have. So that's why we use congestion control here. Okay, the next one, very important content, is what is CWND. The CWND is, sorry, all the thing you need to know about it is unit. So what is the unit of CWND? Do you have an idea? What is the unit of it? We call it window size, right? So what is the window size? We always use byte to describe how large is the window size. And there are two stuff, the CWND and RWND. The first one is the sender size window, like for the sending stuff, and the receive window. So don't worry too much about this part, but all you need to know is what is the unit of the CWND. It's bytes here. And in this lecture, we always talk the CWND is like the multiple times of the MSS. Like you may have some trouble of MSS. What is MSS? Maximum segment size. So what is the maximum size of a packet in the TCP transportation? So if you don't remember it, probably have a look of the LAB5. We have a question related to this one. So basically, it is the maximum packet size of the TCP packet, of a TCP packet. So the CWND is always related to it to describe the size. Okay. Let's have a look of next one. The next page is the congestion event. So what is a congestion event? The first one is the packet loss, right? And the second one is the packet timeout. So if you still remember the TCP stuff, then you may remember in here, when we have a packet loss in the middle side, like in here, the first packet and the second packet, you can see the second packet is lost in the middle, right? So how can we detect this kind of packet loss? We can use fast retransmit mechanism to detect it by receiving 3 duplicate ARC number in here. You can see the 3 duplicate ARC number. Then the host A will be able to detect, oh, probably we lose this packet, then we resend it again. So that we call it congestion event and packet loss. And the packet timeouts, yeah, it should be very easy to understand. Like if we send the packet and the host A will wait for like a couple seconds. And if the host B does not send back any acknowledgement, then host A will consider this packet is timeout and resend it again. So that's all the congestion events. Do you have any question related to this? So make sure you understand what is the difference of packet loss and packet timeout. packet loss, we are talking about the fast retransmit here. So make sure you understand the difference of it because it's very important in the following part. You're talking about triple acknowledgements happens before timeout. Yes, you are right. So if we are using the version of RTT 2.2, so we will have a probably the version is 3.0. We will have a timeout clock for each packet. For example, the second packet, we will set a timer here. It will probably comes to here. If at this point we didn't receive any response for this packet, any ACK for this packet, then we will consider this packet is timeout and we will resend it. But because we have the fast retransmit mechanism here, and we receive 3 duplicate packets, 3 duplicate ACK number, then we already know we have lost this packet, so we resend it. Yeah, so you are right. The retransmit should before the timeout. In that case, it will be always retransmit. Yes. So let's go to the next part. So this part will be the content of the congestion control key content here. The slow start. So what is slow start? Because we are trying to reach and utilize the bandwidth of our bandwidth. So we want to reach our maximum speed, right? So they may have different methods to like detect what is our maximum bandwidth. So the slow start is a method. So you can see the title is bandwidth discovery. So we use the slow start to discover what is our maximum bandwidth. So the idea is very easy. So at first, we will send one packet, like one segment, to the host. And we see if we can receive the acknowledgement of it, then we send double of the size, like let's say 2 packets at this time here. And if we can like receive the acknowledgement of all the content in here, then we can send double again. So in here we send 1 packet, and in here we send 2 packets, and here we send 4 packets. And in the future, if we find no problem with the traffic, there is no packet loss or packet timeout, then we can send 8 and 16 and so on like this. So you can see the curve should be like this in this shape. Did it make sense? So this idea is pretty easy. So we just double the packet size we send every time if we find no trouble with it. So we will reach the maximum bandwidth very soon. Okay, so another method, we call it AIMD. So it's a different method than the slow start. So what is AIMD? You should know what it stands for. So A stands for additive, and I stand for increase, and M stand for multiplicative, and D stand for decrease. So it is basically describe how we control the congestion window size. So for the AI, which means we increase the packets, the window size by 1 every time. You can see this thing here. We increase the packet window size by 1 every time. And when we want to decrease it, we just cut in half here. So that is AIMD. So why should we cut the window size in here? Do you have any idea? Why should we cut the window size here? And in here, we cut the window size by divide by 2 in here. Because there is a congestion event, right? It could be a packet loss. So that is AIMD. So you can see the shape of AIMD is different from the slow start, like in here. So make sure you can understand the slow start and AIMD here. So we can combine these two together. Why should we just use one of them? Why should we only just use slow start or just use AIMD? Because we just want to utilize their advantage and avoid their disadvantage. So what is the advantage for the slow start? You can find the maximum bandwidth very soon, right? And the AIMD will allow us to stay on the maximum bandwidth stable. So if we double our packet size every time, window size every time, we will always exceed that point we will talk about. Let me show you that picture again. Here. So if we have already at this point and we still use the slow start, it will always exceed the loads, and it will always result in packet loss, probably in here. So that's the reason why we want to combine these two methods together. So with the AIMD at this point, at this range, we will reduce the packet loss and congestion event. That's the reason why we want to combine these two together. So in order to combine these two stuff together, we will introduce a stuff we call the slow start threshold. So what is a slow start threshold? Because we need to know when should we switch from slow start to AIMD, right? So we set a slow start threshold. Once we reach this value, then we will switch from slow start to AIMD here, like this. So the next stuff is TCP tail. So what is tail? So basically, it's a kind of method how we use the slow start and the AIMD method. So it describes the detail of how we use the slow start plus the AIMD. So the idea is very simple. So at first, we will have a threshold here. So we will set a slow start threshold, let's say 16. So this one is the initial number of it. So we just already set it. So once we reach 16, we will switch from slow start to AIMD and increase them one by one, 17, 19, 18, 19, 20. And here at this point, we got a packet loss here. So if we find a congestion event here, no matter what kind of congestion event, including the packet loss or packet timeout, we'll go back to 1 at here. But before we go back to 1, we will recalculate the slow start threshold here. So you can see we will recalculate a slow start threshold by divide the window size by 2. So that's why the value is 10. Does it make sense? So we reset the slow start threshold as 10 and begin from slow start again. So slow start will come to the 10 here. Then we switch to AIMD again this way. So that's how it works. Does it make sense? So let me know if you still have any confusion. This is very important. You need to know how we calculate the slow start threshold. Packet loss, is it because of timeout? Not really. We can, yeah, it could be a possible way, as we can see here. So what is a congestion event? The packet loss and packet timeout. So there are two congestion events. In here, I'm talking about the fast retransmit. Sorry for my ugly writing. So in here, we are talking no matter what kind of packet loss, including the fast retransmit or the timeout, we will go back to 1. So it could be a fast retransmit or could be a timeout at here at this point. And yeah, we come to the next method, call it TCP Reno. So what is Reno? Just another like algorithm that how we combine the slow start and AIMD together. So let's have a look of it. So what is the difference of it? As we can see here, we start from slow start just the same, right? And at some point, at this point, we will switch to AIMD and continue to increase the bandwidth, the throughput of it. And in here, we have a congestion event. Here, it says fast retransmit, right? So it's a packet loss here. And we go back to here again. And then keep using the AIMD. And another fast retransmit happens, then we come to here again and keep using the AIMD here. And at this point, you will find some difference than the TCP tail here. So you can see once we have a timeout here, we will go back to 1, just like the TCP tail, right? And we recalculate the slow start threshold at this point. So what is the difference between Reno and Tahoe? Can you specify the difference? Yeah, so the difference is in here at this point. once we have a fast retransmit event, which is the packet loss event here, but the Reno will only go back to here instead of go back to 1. So that's the difference. Can you see that? We can back to the table here. No matter in table, no matter what kind of congestion event, we will go back to 1. But in Reno, we will go back by half here for the fast retransmit. And the timeout, but they will be the same for the timeout event. So is that okay? Yeah, that's all we need to learn for now. So just specify the difference for Tahoe and Reno. For the Tahoe, we don't care about what kind of congestion event is that. We will always go back to 1. But for the Reno, we will not go back to 1 if there is a fast retransmit. So that's the only difference. So I think that should be enough for our LAB5. Let me open the lab. Okay, so in LAB5 should be pretty easy because we don't need to do lots of stuff. There's no coding stuff. All we need to do is just follow the specification of it. But let's have a look of the first one, the revision of TCP congestion control here. So for this 5 question, we don't need to make any submission. You don't need to make any submission for that. So just have a look of it by yourself, but we can have a look of it now. So for this picture, the first question is, what happened in point 1 and 2? So here, we need to know what kind of TCP connection we use, like congestion event algorithm here. Obviously, it's a Reno, right? Because at this point, we have a congestion event happened. Probably it's a fast retransmit here, and we go back to its half, like changing this congestion window to its half, and then keep using IMD again. And at this point, we have a timeout event, right? Then we go back to 1 and start again. So does that make sense? So this one is Reno. So if in Tahoe, no matter what kind of event, we will always go back to 1. So the picture will not be like this. And what happened in this area? Can you call the name of it? Yeah, it is slow start. And what is this part? Other than the slow start, what is the other thing we have learned? Yeah, it's the AIMD. So that's all for the question here. And for the last question we have, what happened after 2 here? So we know at point 2, there's a packet loss, right? So we go back to 1 and start again. So what happened here is, so firstly, is packet timeout, right? So we go back to 1 and we recalculate the slow start threshold, right? To divide the CWND by 2. And the third step is to slow start until we reach the new slow start threshold and AIMD, right? So that's what will happen here. So any question related to this part? We don't need to do any submission for this question. Just make sure you can know everything of this graph. Let me know if you have any doubts. It's very important because if you can understand this graph, every question regarding to this graph, then you will be able to do the contents of LAB5. Okay, so let's go to the exercise 1. The exercise 1, we don't need to do any coding here, so don't worry. Just download all the contents under the exercise 1, including this one, tp window.tcl. Just click it and click the download button. And the second stuff is the what is another stuff here? It's here, window.plot. This one, just click the button and download the stuff. Then we can do the exercise 1. So how can we do it? We just download in our VLab and find the stuff we have downloaded and simply copy the command here. Here, right? Did you see that? Just copy it. And back to downloads, open a terminal here and just paste the command. Yeah, and copy the second line of it, this line, and paste and run. Then you will get a result. So let's have a look of it. So can you see what is the method we are using here? It's Reno, right? Because at this point, we can clearly see that it's a congestion event, probably a fast retransmit here. So we go back to here from around 70 to 35. and use AIMD again, and another event, and go back to here, and yeah, like this. So what is the slow start part? It's here. So we are using the slow start until we reach 100, and it drop back to 50 and drop back to 1. So we can see here at 100 here, probably it is an fast retransmit event here. So we go back to here, and we go back to 50, and then we probably run for less than 1 second, and we drop from 50 to 1. So in here, we can see there should be have a timeout event here, right? So that's what happened. And for the question 2, what is the average throughput by running this command? Probably this one. Just plot this plot. So what is the average speed of it? You can see the red line. It's the average throughput. So what is the value of here? Right? So just have a look of the file, then you can figure out what is the value of it. Does that make sense? And question 3, rerun the script, but set a different congestion window size by changing this number. So what should we do is rerun the script by changing the number from 150 probably to, let's have a look of 50, and run it. And we can plot the stuff. So you can see if we set the congestion window to 50, then we will have no problem, no congestion event here, right? How about we set to 70? And plot. If we set to 70, then we can find, oh, they may have the congestion event here. So you need to change this number and find the threshold of it. Just try so many times and see what is the exact number that may trigger the congestion event. Is that okay? Okay, so to the question 4, we need to modify the code. In here, modify the code by open the file TCP window.tcl and modify it by finding this line. Sorry, because I have already modified it. So you may see a different plot in question 1 to 3. You may find different stuff in for your question 1 to 3, because in here I have already set it as a Reno, right? So if you want to do a table, just delete the Reno stuff and save it, and then we rerun it. Like this. So you can see probably a different output of it for Reno and Tahoe. Okay, so let me know if you have any doubts for exercise 1. So basically just follow the instruction here, then yeah, answer the question. Should be easy. I guess we don't have any question here. Exercise 2. Just download the file tpfairness.tcl by click this button and simply run it in the terminal. So you will find there's no output of it because we need to run another line. Download this file and then copy the stuff and paste. Then you will see the output of it and pull this output into your report and answer the question for in here. So let's see what happened in here. So we have a lot of flow from like host 2, host 3, host 4, host 5, something like that. We have different flow from left to right or from right to left. And they are using the this line to transmit their data. And how they share their bandwidth is like this. So at first, the flow 2 to 3 is connected from 2 to 3. So at first they have the maximum speed because there's no other computer are using this bandwidth. And then here flow 4 to 5 join and start to send something at this point. So the red one, the speed of red one just goes down because if we send a lot of packets at the same time, we will have a congestion event like the packet loss, right? So we will drop from here to here. And once we got more flows joined to the connection, then we will have lower speed. And that's what happened here. Just describe the question and let me know if you have any doubt. Is this fair? This point, we can see they have the similar speed, right? We can't see any flow have a dominant speed than others. So they are in this range, so we can say it's fair. Two to three, not to half. Yeah, you can say it's not to half because we cannot see the slow start or AIMD here, right? Because it's not the details of the speed of it. So you can, it's not a very accurate graph in here to describe how it changes speed. So you can see from this point, it doesn't drop to by half, right? Probably it dropped to here and another congestion event happened and dropped to here again. So, and yeah, because it's not very accurate, since we only have like couple points to describe the speed of it. Okay, so let me know if you have any doubts for this. Okay, since we don't have any problem here, we go to the next one. The next one is similar. Exercise 3. All we need to do is the same. So click the button and download the script. And click this button, download another script. And simply copy the command here. This one. Copy it. And paste and run. It will pop out the window, but we just close it, quit. And then run the plot script. Then you can see the output of it. It's about the TCP link and UDP link at the same time. Right? So you can see the speed for TCP is like significantly lower than the red one, which is UDP. So the UDP speed is dominant. You can see at some point the TCP even do not have any speed. So that's what happened. Just describe. So what happened if we have two connections to UDP and TCP at the same time? It will compete with each other, and the TCP will remain a very low speed at this point. But what if we can set the speed to like higher? Let's say we have very high bandwidth. Let's say 5,000 MB of our bandwidth. So what will be the result of it. So we will have very, very high bandwidth. Then you can see the TCP and UDP, they are not competing with each other. Right? Because here we can see the UDP only use 1000 Mbps. And the TCP at this point has only used 500. So they have enough. And we keep increase the size of it. Yeah, just the same. So you can see the difference if we have different bandwidth. Yeah. So just describe what happened here. This one is just for your reference. You need to run this command. Yes, this one. Include it into your report and answer the question here. So you can see if we are using the TCP and UDP connection at the same time, the TCP will use most of the bandwidth. So that's the reason why if someone is downloading software or the video or the game in your house, then you may find this like you can't even open the web page. That's the reason, because they may use the UDP connection to download the stuff, but you are using the TCP connection to play your video game or open the web page, etc. So there you feel very slow of the speed, and that's the reason. So that's all for our lab. So let me know if you have any doubts. And feel free to stay here until the end, because I will stay here. If you have any doubt, just send it to me. Or you can even share your screen. But if you don't have any problem, yeah, just feel free to leave. And thanks for coming. We'll see you next week. I will stop the screen sharing and the recording from now. So if you have any doubt for your assignment or for the lab, just let me know.